Welcome to the Explainer. Today, we're building the ultimate mathematician's toolkit. Now, this entire guide is actually based on some incredible work created by Mrutyunjay Kumar, who is a TGT math teacher over at Kendriya Vidyalaya in Kagaria. So a huge shout out there. Look, if you've ever stared down a complex math problem with an x squared in it and felt, that slight wave of panic, you are absolutely in the right place. We're going to decode, deconstruct, and just completely master quadratic equations. By the end of this, you won't just be solving these things, you'll literally be predicting their behavior before you even pick up a pencil. Let's get into it. But okay, before we look at any formulas at all, we've got to establish the golden rule of this universe. And that golden rule is simply the number 2. What does that mean? Well, it means every single quadratic equation in existence has exactly 2 roots, no more, no less. You're never, ever looking for 3 answers, and you're definitely not settling for just 1. You're always hunting for exactly 2 values that satisfy the equation. Keep that locked in your mind.
Moving right along to the foundation, equations versus polynomials. Notice the precise shift in language here, guys. When you're dealing with a quadratic polynomial, meaning an expression without an equal sign, you're looking for its zeros. And a polynomial can have a maximum of 2 zeros. But the very second you take that polynomial and set it equal to 0, boom, you've created a quadratic equation. The terminology shifts completely. We stop looking for zeros and start hunting for roots. And just like our golden rule just stated, an equation is going to give us exactly 2 roots.
All right, here is the basic DNA of every quadratic equation you'll ever come across. ax squared plus bx plus c equals 0. This right here is the standard form. But, and this is a huge but, there's a crucial little condition right there in the brackets. A absolutely cannot be 0. Why? Well, think about it. If a were 0, that entire x squared term would just vanish. Poof, gone. And without an x squared, you don't actually have a quadratic equation anymore. You literally just have a straight line. The x squared is the engine driving this whole machine.
Let's open up our toolkit. Tool 1, the factoring method. So this method is basically a brilliant little 3-step algorithm. First up, you take your first coefficient, a, and multiply it by your constant at the very end, c. Second, and this is where you put on your detective hat, you need to find 2 magic numbers. Now, these numbers have to multiply together to equal your a times c result, but they also have to add up to perfectly equal b, your middle number. Make sense? Once you actually find those 2 magic numbers, step 3 is simply splitting that middle term b into those 2 new pieces and factoring them out. And honestly, this brilliantly illustrates how the logic holds up even when the numbers look, well, downright terrifying. Just look at the example we have here. We've got a square root of 3 just sitting right in the middle. But don't panic, our rule doesn't change. We need 2 numbers that multiply to 12 and add up to 5 root 3. Now, since they add up to something containing a root 3, it stands to reason both of our magic numbers must also contain a root 3, right? We know that root 3 times root 3 is 3. So to get our total product up to 12, we just need the remaining parts of our numbers to multiply to 4. How about 4 root 3 and 1 root 3? Look at that. They multiply to 12, and they add up perfectly to 5 root 3. The logic literally never breaks down. Moving on to Tool 2, the ultimate quadratic formula. Enter the Sridharacharya rule, which you probably know better as the quadratic formula. Guys, this is the master key. It really doesn't matter how ugly, how decimal-filled, or how impossibly complex the equation looks. If you just plug your a, b, and c values into this exact formula, it will forcefully extract those 2 roots for you. It's x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And see that plus or minus sign? That right there is exactly why this machine spits out 2 distinct roots. All right, next up, decoding the discriminant, predicting the nature of roots. Look really closely at that quadratic formula we just went over. Right inside the square root, there's a very specific piece of math, b squared minus 4ac. We actually call this d, the discriminant, and it's like a mathematical oracle. Just by calculating this one tiny piece, without doing any of the rest of the heavy lifting, we can completely reveal the nature of our roots ahead of time. The rules for this discriminant are remarkably simple. If your discriminant, your d, is greater than 0, meaning it's a positive number, your equation is guaranteed to have 2 real, completely different roots. If d is exactly 0, well, the equation will still have 2 real roots, but they're going to be identical. They are perfectly equal. And finally, if d is less than 0, so a negative number, you can literally just stop right there. The equation has no real roots at all. Why? Because you can't take the square root of a negative number in basic real number math. Simple as that. So why is this so crucial? Well, this is exactly how exam papers love to test you. They'll throw questions at you like this one. Find the missing variable k if this equation has equal roots. The very second you read those words, equal roots, your brain should immediately start yelling, d equals 0. It's a dead giveaway. You just calculate b squared minus 4ac, set that whole thing equal to 0, plug in the numbers you do have, and solve for k. You're essentially using the nature of the roots to hack the problem and work backward.
All right, time for the final boss, conquering word problems.
Let's look at a really classic setup. It goes like this. The sum of two numbers is 15, and the sum of their reciprocals is 3 over 10. What are the numbers? Okay, at first glance, this doesn't even look remotely like a quadratic equation. It just sounds like a riddle. But the secret here is the power of translation and substitution. We start by just assigning variables. Let's let the numbers be x and y. So x plus y equals 15. Easy enough. The sum of their reciprocals just means 1 over x plus 1 over y equals 3 over 10. Now here's the magic trick. How do we get a quadratic equation out of something with two variables? We substitute. From that very first equation, we know y actually equals 15 minus x. If we take that and plug it right into the second equation, suddenly we only have x's. And the moment we find the common denominator and multiply it all out, that x squared naturally appears. And boom, we are right back in familiar territory.
Let's tackle another legendary word problem format. Find two consecutive odd positive integers whose squares sum to 290. Honestly, the trick here isn't even the math. It's entirely about how you set up the starting line.
A ton of people make the mistake of assigning the variables as just x and y. But think about odd numbers for a second. 3, 5, 7, 9. Notice the pattern? They always jump by 2. Always. So if your very first odd integer is x, the next consecutive odd integer absolutely has to be x plus 2. The problem tells us the sum of their squares is 290, so we simply write x squared plus the quantity x plus 2 squared equals 290. See what we did there? We just translated an entire confusing English sentence into one beautiful, clean algebra equation.
Finally, let's look at the specific problem type that haunts the nightmares of math students everywhere, the two-digit number word problem. You know the ones. They always talk about digits interchanging or swapping places. So how do we build a truly reliable setup for this? To beat this boss, we really have to break down how our base 10 number system works. Think about it. If you have a two-digit number, say 53, it's actually 50 plus 3. The digit in the tens place is literally multiplied by 10. So let's say your tens digit is y, and your units digit is x. Your original number is written mathematically as 10y plus x. Now, if the problem says the digits are reversed, well, that x is suddenly sitting in the tens place, so the reversed number is just 10x plus y.
Let's see this in action and translate it into a flawless equation. The problem says 18 is subtracted from the number, the digits are interchanged. Guys, we literally just read it left to right and turn it into math. The number is 10y plus x. 18 is subtracted, so we simply write minus 18. Then it says the digits are interchanged, which just means it equals the reversed number, 10x plus y. Put the whole shebang together, 10y plus x minus 18 equals 10x plus y. Boom! From there, it's just basic algebra cleanup to find your roots.
And there you have it, folks. You know the golden rule of two roots. You know how to factor the absolute trickiest square roots. You've got the master key formula, the power to literally predict the future using the discriminant, and the solid logic to decode any word problem final boss they throw at you. You now possess the ultimate mathematician's toolkit. The only question left is, the very next time you come face to face with an impossible-looking equation, which tool are you going to reach for first?